here we have measured the values of velocity of the link AB and velocity of the link BC, which we measure from this line, and we will be getting like 3.4 meter per second. And for CD, that is perpendicular to this link, we have drawn, and the value is 3.9 meter per second. Now we have to draw the acceleration diagram. So for that we will have to first mark the fixed links AD. I forgot to mention about the fixed links AD in the velocity diagram, and the same has to be done. We have to keep both the fixed links at the same point in both the velocity diagram and the acceleration diagram. This is the velocity diagram, and now we have to draw the acceleration diagram. Okay, so again we have to fix the point AD. Yes, so yes, we have fixed the point AD. Now we have to first draw the centripetal acceleration for the link AB. And please note, for drawing the acceleration diagram, it should be always parallel to the links. Here the AB is like this, so the centripetal acceleration should be parallel to the links. Okay, now we have drawn parallel to the link AB. Now we know the value of the centripetal acceleration which we got from here. is 55.1 meter per second square. So the magnitude and the direction for centripetal acceleration is given. We know it. We have calculated it. So we have to mark 55.1, right? 55.1 exactly. So we have got the point here. So from here, now to draw, it's a very important point. To draw the tangential acceleration, we know it is always perpendicular to the direction of the centripetal acceleration. So we have to draw perpendicular, but here it is given in the problem. The link AB is having an angular velocity counterclockwise and an angular retardation. So this is retardation. For retardation, and for retardation we have to draw tangential to the centripetal part, perpendicular, and it should be downwards, and the value we also calculated the value. It is 13 meter per second square. So it is 13 meter per second square. So we have got this is the centripetal acceleration, this is the tangential acceleration. So in order to complete the diagram, we have to extend from this point where the acceleration part for AB ends centripetal and the tangential part ends. We have to again draw parallel to the link BC. You have to draw parallel to the link BC. Now the centripetal acceleration for link BC which we got is 17.5 meter per second square. That is, from the velocity diagram we got the value for velocity for BC is 3.5 meter per second, and so equating that as velocity of BC 3.4 and the link BC is 0.66 meters, so we are getting 17.5 meter per second square. So we have to draw exact 17.5. 17.5, we have marked 17.5. Again we have to continue the same step which is mentioned here. We have to take the tangential acceleration, which we have to draw perpendicular, but it is not given the links BC and CD whether it is acceleration or retardation. Then again we have to take from this point, we will draw perpendicular, but this time in both directions, because we don't know to which direction it is going, so we just drew in both directions. Now we have to draw the centripetal acceleration of link CD, which is parallel to the link CD. So again taking parallel, so we know the value of centripetal acceleration for the link CD. We can easily calculate. We'll be drawing that. We know the tangential acceleration for the link CD equal to 3.9 the whole square divided by 0.56. This 0.56 is the distance of the link CD, and 3.9 is what we got from the velocity diagram. This is the equation as we mentioned earlier. So we have to draw that magnitude, that will be 27.2 meter per second square. So this has to be .27.2. So we got the point here. Again we will have to draw the tangential part, which we do not know in which direction it is going, so that we will draw it both ways. But here we got the intersection point between all these links, so this is FT CD, this is FC CD, and from here what we get is the tangential part of this link BC, the link BC, that is FT BC, and this is FC PC. So this is FC AB and this is FT AB. So all the tangential, unknown tangential acceleration are got from the diagram. We can measure and find it out. FTCD. This is FTCD. Yes. And you are clear about this. This distance is FTCD. This distance is FCCD. This distance is FTBC. This distance is FCBC. And this distance is FTAB. And this whole distance is FCAB. So we will measure and find the values of all this. We will get this is 44. FTCD is 44 meter per second square and FTBC is 34 meter per second square. Not 34, it's 24 meter per second square. Okay, so we have completed all these parts. Now we will have to draw the links in the acceleration diagram. For that we have found the point C and the point D. So we will have to just finish the links in the acceleration diagram. Join from the point A to, yes, first A to B, right, A to B, and from here to C and C to D. So the red line represents the links in the acceleration diagram, and now we have to mark the center of mass of each links, the point where the center of mass of each links are acting. It is given in the question. The center of mass of the link AB is lying at 200 mm from A. So here it is, this is the link AB and it has to be 200 mm from this point. So we have to take proportion. We are getting around 5.5 centimeter in place of this 500 mm. So we have to take the distance 200 mm from A proportionately in the diagram to find the center of mass. So it will be around 22.6 in the diagram. .6 taking proportion, you will be getting 22.6. So mark this as G2 or the center of mass of the link AB, and again nothing is mentioned in the problem about the center of mass of the link BC and the link CD. So we will take it as the midpoint of BC and CD, that is the midpoint, and the midpoints has to be mentioned here also. So the BC, the link will measure, it will be like 3 centimeters. So 1.5 centimeter will give the midpoint or the center of mass of the force acting at link BC, and it can be represented as G3. Similarly, the link CD will be 5 centimeters measured in the acceleration diagram. So it will be at 2.5 the midpoint, and that is the point is G4. Okay, now again we can join the midpoint G3, which is located here, to the fixed link, and from the fixed link now we can measure the angles. That is the angles of each links from the fixed link. So for CD it is around 41-42. So we can again mark to the angle up to this link, right? So this has 4, and similarly we can measure up to this link, and that is 3, and from here this is 2, right? So by measuring you will be getting 180 plus 42 will be 222 degrees for the center of mass of link CD, that is G4, and again it will be for link G3 it is 42 around 58. So 180 plus 58 gives 238 degrees for G3, and for the link AB it is 73.5, that is for the center of mass of link AB, that is G2, it is 73.5, which we get from the measurement. So adding 180 plus 73.5 gives 253.5 degrees. Okay, so I hope you are all clear with this. So this is the angles from the fixed link to each of the center of mass of the links, which is measured as 222, 238 and 253.5. Now also can be the center of masses. The values of the center of masses can be measured from here. So it is 22.5 for G2. So 22.5 is the value for G2, 22.5. So as it is in the acceleration diagram, it will be 22.5 meter per second square. Similarly, from the fixed length, measure the value up to the point G3. It will be around 52. So G3 equal to 52 meter per second square, and for G4 it is 22.6 meter per second square. So our measurements which we take from the fixed link up to the center of mass of each links. Okay, now we know the forces acting on each links, that is F2. Forces acting on each links will be equal to mass into acceleration. Mass into acceleration. So for the link 2, the mass is given, it is 3.4 kilograms, 3.54 kilograms into the acceleration. So this acceleration is taken up to the point of the center of mass, that is, this is the acceleration to the center of mass through which the force acts. Is that clear? So for G2 it is 22.5. Sorry, this will be around, this value will be around 24. So 22.6. G4 is G4 is 25. G4 is 25 meter per second square. It is 25 meter per second square. So for F2, we know the acceleration component is 22.5 meter per second square. So you have to multiply that, that is 22.6, should be around 80 Newton. It will be around 80 Newton, and the angle to which it acts, which we measured, is angle 253.5 degrees. Okay, and for similarly for F3 is m3 into the acceleration, that is G3. So here m3 is not directly given, stated 4.2. The question, mass of the links BC and CD is 4.2 kilogram per meter length of each link, and so, and we know for BC it is 660 mm, and by substituting that we will get 4.2 into 660, we are doing it in meters, so 0.66 into, which means m3 equal to around 2.77 kilograms. So F3 equal to 2.77 into G3. We got it as 52, right? Into 52, we get 144 Newton and is acting at an angle 238 degrees. And for F4, similarly it is the mass M4 into G4. So M4 equal to 4.2 into 0.56. M4 gives 2.35 kilograms. So F4 equal to 2.35 into 25, which we got from here, 25 to G4. It will be around 60 Newton and is acting at an angle 222 degrees. Now we will have to find the inertia coupled in order to complete the dynamic force analysis. We have calculated the forces. Now we have to consider the inertia coupled also. So here is given the angular retardation for link AB, that is alpha 2, is 26 rad per second square, and it is retardation. Here the angular velocity is counterclockwise and the angular acceleration is actually retardation. So the acceleration